Hello, guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today, we're looking at the third and final question on the 2021 midterm for heat and mass transfer. It's a relatively straightforward heat exchanger question. However, a lot of people went wrong and solved it incorrectly. So, what we're going to do today for a change is actually solve it in the incorrect way, see if you guys can spot the problem as we're doing it, and then obviously solve the correct way. All right, so problem statement reads like so. Water at a flow rate of 3 kilograms per second is heated from 35 to 55 degrees Celsius in a counterflow double pipe heat exchanger. Steam is used as a heating fluid at a flow rate of 1.8 kilograms per second, entering the heat exchanger at a temperature of 95 degrees Celsius. The overall heat transfer coefficient is 1420. The specific heat capacity of water and steam is 4.18 and 2 kilojoules per kilogram Kelvin respectively. Calculate the surface area of the heat exchanger. So this is a classic delta T log mean problem, right? So we have a double pipe heat exchanger. We're going to draw it as simple as we can, just as a simple box. And inside this box, I'm going to put steam going to one side and liquid water going to the other. Reason being, it is clearly said this is a counterflow heat exchanger, right? So I'm going to have something like this. Obviously, steam and water. Steam is also water, but you get what I mean. So we know that this guy is entering at 95 degrees Celsius, and we know that this guy is going from 35 to 55. Great. What else do we know? Well, we know the mass flow rate of this guy is 3 kilograms per second, and it has a C sub P, right, a capacity of 4.18. I'm going to go ahead and convert this into joules for both the steam and the liquid water. So 480 joules per kilograms per Kelvin. And then here in the steam, we have information for it too. It is 1.8 kilograms per second, and the C sub P here is 2000 joules per kilograms per Kelvin. Okay, so what is the game plan? Well, the game plan here is that we are going to use the natural log mean difference in temperature to be able to find out what's the area, because we know the heat is going to be exchanged inside this heat exchanger is the area through which the two fluids can exchange heat times the overall heat transfer coefficient for this system, which was given, times the correction factor, if any. Right? If we do have any correction factor, we need to account for it. The problem didn't say so. We can go ahead and say this is going to be 1, and the delta T log mean. Okay, so first things first, nothing is said. So when nothing is said, we're assuming this is 100% efficient. And then to be able to solve this, right, what I'm trying to solve is for area, so that means that my area is just going to be the heat exchanged through in this device divided by delta T log mean. Right, we can find this fairly easily. We can find, this was given, and the overall heat transfer coefficient was given. So the only thing we need to find is the delta T log mean to be able to solve this problem and be happy about it. So how would we do that? Well, the amount of water, well, the first thing, obviously, just to be sure, we know energy is going from the steam into the water, right? This is the hot fluid and this is the cold fluid, so we know it's going from top to bottom in this drawing that I did. And we know how much water, how much energy water requires to go from 55 to 35, right? We know that's related to the mass flow rate of water times the specific heat capacity of water and the delta T in question. So in this case, it's 3 times 4180 times the 55 minus the 35, which gives us 200, what did I get? 250,800. Okay, and then unit-wise, this is going to be joules, but we can be sure, because we have kilograms per second times the heat capacity, so joules per kilogram per difference in temperature. And then here, difference in temperature in Celsius, which is equivalent to a difference in temperature in Kelvin. So indeed, kilograms and kilograms, Kelvin and Kelvin, and I said joules, but it's actually watts, right? So watts, joules per second. So this is in watts. Okay, so what next? Well, to be able to find, well, we already have these two. What we don't have is this. To be able to find that guy, I would need to find this fella here, right? And this is where things go wrong. How am I finding that guy? Well, first instinct would be, because all the energy that the water is absorbing, that is because all of this guy here is coming from steam. Well, I can assume this is coming from the difference in temperature of steam. So as steam is losing energy, it's giving away to water. So that means that the energy given away by steam is going to be the 250, 800, which has to be equal to the mass flow rate of steam times the specific heat capacity of steam and the delta T of steam, right? We have this fella here, we have this fella here, so we can find what is the delta T of steam, and we can find what is the output temperature there. So that would be easy for us because this means that, the delta T, let me write this in blue, the delta T, which is just 95 minus whatever T hot out, or whatever is being outputted, is just going to be the 250, 800 divided by the 2000 and by the 1 point, what was it? 1.8, 1.8. Okay, and this is going to give me a number, what do I get? 25.33. So 25.33 degrees Celsius. So this would be, the output temperature of the steam after it gave away all the energy to the water. And then this, hopefully already, you've seen a problem already, but let's say you didn't, and we keep going, right? So let's pretend all is good. So let me go ahead and copy this, or just copy it, but I won't use it for now. So let me go ahead and say this is 25.33. 25.33. We're oblivious to the problem, and we just keep going, and we try to find the difference in temperatures now. So the difference in temperature here is going to be 40. So the difference in temperature on the left-hand side of my drawing is going to be 40, and on the right-hand side, the difference in temperature here is going to be 9.67. Okay, so if I want to find delta T log mean, this is very straightforward. All I need to do, let me do it over here. Delta T log mean will just be the 40 minus the 9.67 divided by the natural log of 40 divided by 9.67. And this gives me 21.36 Celsius degrees Celsius. Okay, so if this is the case, then, well, I have everything I need. I can plug it in here. I have my 250, 800. I have my overall heat transfer coefficient, which was given to be 1,420, so 1,420, and I have the delta T log mean I just found 21.36. Unit-wise, everything checks, everything's beautiful, and this tells me that I only need about 8.16 meters squared to be able to have this water being heated up. Well, this is what a lot of people did. This was their final answer. Why is that incorrect? Well, you could have noticed that when we did it here, when we found this number here, that was incorrect, or when we're doing the differences here, right? Because this would be 95 minus 50, which is 40, but this would be 25 minus 35, which would be negative 9.79, 16.7, and that would be, might strike you as odd. What is the problem? Well, if the output temperature of the hot was 25, note that the hot fluid is now colder than the cold fluid, right? So the Earth's law tells us that instead of heat flowing this way, heat would have to flow this way. So in the beginning here, it's actually flowing like we would expect, right, downwards. At some point, it would change and flip and start going upwards. Let me change colors. So when we do the flip to orange, right? At some point, it would flip and start going upwards. Now, that is physically impossible, right? This is, we're assuming no heat is entering or leaving. This is an adiabatic heat exchanger. And this would be impossible because for this guy to be able to give energy to this guy, it needs to be at a higher temperature. For it to be at a higher temperature, it needs to absorb energy, and it's absorbing energy precisely from this guy. So what would happen is the maximum it could actually leave over here is 35. Right? That's the maximum theoretical it could actually leave. So as the temperature is getting closer and closer to each other, we know the heat transfer is getting smaller and smaller, and then in the infinity, they will find themselves at the same temperature. So if this were the case, what would be our actual heat exchanger, right? So let me continue with the problem. That's one of the problems. The second problem is that we know that steam does not change, um, does not give away energy and changes temperature unless it fully converts into liquid, right? So when it reaches its boiling point, or actually at boiling point, it's going to give away latent heat during the saturation mix phase inside the dome, for those of you who remember thermodynamics. And then once we reach the saturation line, then we have saturated liquid. We don't have the last droplet of steam, then it's going to start decreasing in temperature. So that's another reason to be skeptical about the way that we just solved it. But what would be, let's forget that steam cannot change in temperature for a while. Let's assume it is indeed giving out energy due to the difference in temperature. Let's see what would be um, the maximum temperature that the steam could give to the water. Okay, so we know the theoretical maximum it can leave is 35. So that means that our mass would be something like this. The energy the steam is giving as it's losing temperature equals the energy the water is absorbing. So steam has 1.8 kilograms per second at 2000 heat capacity, and it's going from 95 down all the way to the 35 that we said was the maximum theoretical, right? And then on this side here, we have water coming at 3 kilograms per second and 4180 specific heat. And then it's entering at 35, was it? Yeah, 35, and then it's leaving at what? I'm not sure. So what is my cold output if it's entering at 35? So note what I'm doing here. I'm assuming this, maximum theoretical one, and I'm trying to find out what is the maximum I can output under these conditions. And we solve this math, we get the maximum cold out we can possibly have is 50, what did I get here? 52.22. Okay, so the heat exchanger that we saw in the beginning, the one that let me see if I still have it here. Here you go. This one here, right? This would be impossible under the assumptions we made in the beginning, right? It can only happen if this guy here is 52.22, and this is only going to take place if our heat exchanger is 100% efficient, right? This is the maximum theoretical possible. Or if the area of this heat exchanger is infinite. That's another possibility, right? So now that we solved the wrong way, let's say, let's solve it the right way. So let's do um, correct way of doing it. Okay, now we go back to the idea that steam is not going to change its temperature unless the whole mass becomes liquid, right? Saturated liquid. So therefore, we don't expect any change in temperature on the output of the steam. This is where logic kicks in when solving this problem. And then when you do this, you simplify because you have one step less, which is finding the outputs of the steam. But then it simplifies. You also simplify the solving hips because you're going to have 60 on one side and 40 on the other side there. And there you go. Now it's easy for us to calculate our delta T log mean. Once we do that, we can find out what is the area required for this heat exchanger, which can physically happen, can physically take place. So what is the delta T log mean? Well, it's going to be something between 40 and 60. If it were, simple mean, it would be 50. But in this case, it's going to be something very close to 50. Bit lower than 50, but very close nonetheless. 60 over 40, and this turns out to be about 49.33, about 49.33 degrees Celsius. And now we go, home run. If you want to find out what's the area of this, we know it's requiring, remember, doing Q over U delta T log mean. Our F was assumed to be 1, so this is 250, 800 watts divided by 1,000, what was it, 1,420, 420, and this guy here is 49.33 degrees Celsius. In terms of units, let's just put the units here. So this gives me 3.58. Let me just double check on the units. Where's my green? So we have watts on the top there, and then the unit for the overall heat transfer coefficient is the same as the convective one divided by difference in temperature, and over here we have a difference in temperature from the delta T log mean. Remember, this is coming from this guy here. If we were to convert both of them to Kelvin, 273. These would still go away, would still be 40, right? So this would still be 40, this would still be 60, even if in Kelvin. So therefore, the difference in temperature in Kelvin or in Celsius the same. This guy goes away, this guy goes away, and we're left with that guy. So good. And this is our actual answer to this problem. Right? So I hope you guys noticed the problem as you were solving it. If you didn't, make sure to watch this video step by step, understand the process, the thought process behind it, and reasons for which the other way is incorrect and this one is the way to go. All right? If you have any questions, as per usual, leave them down in the comments. If this video helped you out somehow, consider giving it a like, and we'll talk soon.